Let's step out of the pristine data center. In this module, we track IT infrastructure as it moves into the physical environment: concrete walls, air conditioning ducts, and under the streets of a modern city. The core of this physical integration is the Building Management System, or BMS. You can think of it as the central nervous system of any smart commercial building. A BMS strips manual control away from human operators. It uses sensors, schedules, and programmed rules to automatically manage heating, cooling, lighting, and security access. In this session, we will build out the 4-layer IT architecture that makes this automation possible, examine how these systems scale into smart cities, and flag the traps you will see on your upcoming exam. Before we begin, note that standard cloud architecture principles do not fully apply here. When dealing with life safety and physical hardware, the priorities change. Navigating this environment requires more than data capability. To build a system that works, we have to account for the rigid constraints of physical hardware and the unpredictable patterns of human behavior. We will map this out by building a smart building's IT stack from the ground up. This schematic maps out the architecture. Look at the very bottom. These are the field devices: temperature sensors, air valves, electrical meters, and light switches. Because these devices directly measure physical reality, like the rotation of a fan or pipe pressure, they operate with reaction times measured in strict milliseconds. Moving up one level, we find the field controllers. These are small, dedicated computers, typically installed one per physical zone or equipment subsystem. A field controller runs a continuous control loop. It compares the reading from a sensor against a configured target, known as a set point, and then commands an actuator to adjust physical outputs until the reading hits that target. While field devices detect changes in milliseconds, controllers process the control loop and issue commands in seconds. Together, these bottom 2 layers form the unthinking reflexes of the building. They react instantly to physical changes, but they have no broader context of what the rest of the facility is doing. A typical commercial building contains hundreds or thousands of these local control loops. So how do disparate controllers pass data to each other? They use specialized industrial communication buses. The dominant protocol for modern commercial HVAC systems is BACnet. As an open standard, BACnet allows equipment from entirely different manufacturers to communicate without requiring custom integration. Alongside BACnet, you will frequently see Modbus. It is an older, simpler protocol, but it remains highly reliable and is widely used for connecting heavy industrial equipment and energy meters. In European deployments, KNX is the common standard, particularly for managing lighting and shading systems. This brings us to a massive conceptual trap in systems design, confusing the internal building communication with external power grid communication. You will encounter protocols like OpenADR. It is strictly used by the external power grid to send demand response signals to a building, asking it to reduce power. The boundary is absolute. Grid-side protocols talk to the building as a whole. Field-side protocols talk to the physical hardware. You never mix the two. Back to our architecture chart. Above the controllers is the supervisory server. Here, building-wide schedules and cross-subsystem rules live. The response time steps up to minutes, coordinating the entire facility's rhythm rather than a single thermostat. This raises a classic architectural debate. Why pay to maintain an expensive supervisory server physically on site in a basement room rather than hosting that logic in the cloud? The answer is life safety. If a fire system detects an alarm, the HVAC system must immediately stop pushing air to contain smoke, and the access control system must unlock emergency exits. If the building's internet connection fails, any cloud-based safety logic becomes completely inaccessible. The internal network must keep functioning in an isolated loop. This is a pure application of edge computing principles. By keeping the supervisory server on site, the building prioritizes operational continuity over centralized processing power. In critical infrastructure, continuity is the primary metric of success. A system that keeps working locally during a network failure fulfills its purpose, while a high-speed system that goes dark is a safety risk. When this architecture functions correctly, a fully automated building management system reduces energy use by 20 to 40% compared to manual control. This chart illustrates the reduction. The dashed orange line is a fixed manual schedule. The solid green area is occupancy-based control. Notice the sharp drop in the middle of the green chart. As occupants leave for lunch, the system instantly throttles down HVAC and lighting. But this efficiency is vulnerable to a phenomenon known as process drift. This occurs because of how human beings actually interact with thermostats. When an occupant complains about temperature, facilities teams apply a temporary manual override in the software to fix the immediate comfort issue. The problem is, they frequently forget to remove that override. Over months and years, hundreds of these manual overrides accumulate across the system. Eventually, large portions of the building effectively run on manual control again, negating the automation. We also see sensor drift, where physical hardware falls out of calibration. A temperature sensor that reads 2 degrees off will force the controller to hold the entire zone at the wrong set point. The solution is recommissioning, a scheduled system of 15 isolated buildings to a single centralized dashboard. Connecting those 15 buildings yielded an immediate 8% reduction in campus energy use during the first year. The interesting part is that the dashboard did not change a single automated control algorithm. It simply provided visibility, exposing long-forgotten human errors, like air handling units that had been overridden to run 24 hours a day. This illustrates the final step in our architectural model, the city data platform. It operates on a hub-and-spoke layout, where individual systems like buildings, transport, and waste publish their data streams to a central municipal hub. You might assume the main challenge in deploying a smart city is bridging all these different data protocols. It is not. The true bottleneck is governance. These systems are owned by different private developers, utility companies, and government agencies. Navigating competing commercial incentives, data privacy laws, and security access is far more complex than writing an API. They start by integrating one narrow, highly valuable data link between two systems and grow outward from there. Let's transition into exam preparation. There are 4 specific conceptual traps in this module that consistently catch students off guard. Trap number 1 is the architecture trap. If an exam question asks why the supervisory server is located on site, the answer is never about latency or server cost. The answer is exclusively continuity for life safety functions. Trap 2 is the metric trap. You need to know the baseline performance metric. A well-designed, fully operational BMS reduces a building's energy use by exactly 20 to 40%. Trap 3 is the city trap. The primary obstacle to integrating a smart city is governance, getting independent organizations to share data, not technical bridging or protocol translation. And Trap 4 is the anomaly trap. If you are presented with a case study where energy consumption slowly creeps back up over a 5-year period, identify process drift and override accumulation as the culprit, not hardware failure. Notice the common theme across all of these traps. In physical IT systems, human factors and physical safety always override raw processing power. You now have a complete model of the smart building stack, from the millisecond reactions of field devices all the way up to the governance of municipal data platforms. In Module 6, we will shift focus to cloud architecture and multi-region deployment, which is generally considered the most demanding section of the term. But as we move into the cloud, keep this lesson in mind. No matter how abstracted or complex a network gets, it eventually has to connect back to physical reality. See you in the next session.